I'm looking at ellipse drawing mechanisms from the book Mechanisms for the Generation of Plane Curves. And the mechanism I'm going to do in this video is the crank slider, figure 170. And in fact, we'll see how that is very closely related to the previous linkage in figure 169, the Archimedes triangle. So here's the Archimedes triangle. We have just a line length L, and A is able to slide up and down on the y-axis, and B is able to slide backwards and forwards on the x-axis. We can watch watch as T, the location of B moves. We can watch the now. We could notice the following. If we take the midpoint of the line and join that up to the origin, and watch as we move around, we see that in fact this triangle EDB is simply a crank slider. There's a crank and there's a connecting rod, there's a slider going backwards and forwards. So there's a different mechanism, but it's achieving exactly the same motion. Let me just draw that mechanism. Basically this. Two lines, these have to be the same length. About L/2 as far as the previous one is concerned. Point again. That distance A up this link. Now notice if we put a point on the axis and make that point lie on this link using the constraint here. So we can see as we move, see the line EC is behaving exactly as it did in the triangle model. Now we're going to drive this. Actually, let's just drive it with an angle. Put a theta in there. And so now we could look for the locus of D as theta varies. Now I'm going to actually get theta just to vary from minus pi/2 to positive pi/2. And let's look at the locus. As theta varies of D. We're seeing we're getting half an ellipse. I'll show you in a second why I went with that half ellipse, but we can watch the mechanism move and give us that chunk of ellipse. That's the reason I didn't want the more than half. We can see what happens in a minute. First, let me look at the equation of that. It will of course be exactly the same equations we had before. So there we go. That is in fact an ellipse, as we can see. It's got an x squared and a y squared term, although we'd have to do a little bit of algebra to break those out from there. Notice if this is at any point really on the line, but if we create a point somewhere else, but attached rigidly to that line. Let's do it by giving a couple of lengths here. And then F. Let's have a look at the locus of that. We did an interesting version there. It looks like we're getting a completely straight line. Let me just change some of these parameters. That was a very fortuitous selection of parameters. In fact, that straight line was a degenerate ellipse, I believe. Let's just check. And indeed, if we look carefully at that result, we can see that the square root is just, if you look inside, is just a constant for the cross term, the term xy. This ellipse, of course, was not lined up with the axes, but we can see that any point rigidly attached to this link BC is going to give an ellipse, albeit in some circumstances, degenerate one.